So today we're going to talk about how you can best leverage your i.MX8, how to build a platform, essentially, and different overall key points that we wanted to highlight for this presentation. And starting with some introduction, that's my name, Adriano Rava. I'm the solution director. I work at Witekio. We used to be named Adenio Embedded back in the days. We're part of Avnet, and I'm based in Bellevue, Washington. And in that talk, what I want to highlight, basically those three key points, the feature that we think you should not miss out and really leverage as much as possible, how that ties into the i.MX8 and part also of the 9 NPU family, and using Yocto with that. And after that, how to build a long-term platform, because you'll see that ties a bit into some of these concepts as well. The first step is getting started. I assume most of you already getting started with the i.MX8. If you're here, you probably know what this is, but I'll try to sprinkle some of what we think are the best practices here. So enabling your software team, again, software guy. Enabling also a faster and quicker bring up of your platform and optimize that platform. And we'll start with a rough overview of the i.MX8, very high level. So for us, that's a great platform because it's very versatile. You have different IOs combination. You have from very low power to very performant. You have a range of security features that you can use. You have, so as I mentioned, low power from like the ULP to the Quad Max without neural acceleration, all of these different options that you have while having a similar core for the i.MX8. And in general, it's a proven and well-designed and working architecture. We use that in a lot of different projects with our customers. It's just one that works well and we're happy to use. Some form factors they can use, for example, the Max board, which is more like a Raspberry Pi type of form factor that's production ready. The SMARC modules, different vendors, but having that SMARC form factor, as well as the OSM, which is a smaller form factor. We need something a bit smaller for your device. And with that, some options to help you choose. Of course, one axis is the graphical acceleration and graphic support. So Viventi GPU on some of those. That can use with OpenGLES, Vulkan. Performance and energy saving are one of the advantages of Vulkan in general. The video and audio acceleration as well. So here, typically, if you have a lot of video requirement, and whether that's input or output, you can use all the internals of the processor, and typically through GStreamer plugins to accelerate that and make sure that you can achieve larger throughput. One recommendation on the hardware side is just to make sure that you're using the right hardware interfaces as well, because there's both the software side and the hardware side in terms of bottleneck that you need to consider. You have some image processing acceleration that's also available, and DSPs, again, depending on the processor that you use in that range. AI, very important. You have the i.MX8 Plus, which has a dedicated NPU. If you're not on that processor, you can still leverage hardware acceleration on the GPU-enabled one. And another one that's interesting if you have a hybrid architecture is to use an NStreamer, for example, which lets you, through GStreamer in a way and custom plugin, essentially accelerate the AI inference using an AI accelerated device. Cryptography through the CAM, very important. I mean, that's pretty much everywhere now, and that's something that you can accelerate, and that will be partly out of the box also accelerated. And in general, knowing your processor and what's available from a single to 6 Cortex-A and different type of Cortex-A within that range. So you have the 53 for the i.MX8 and the 72. Those work differently, so the frequency is not the only factor you will look at, but also how the architecture impacts your requirement in terms of performance. Now you get your platform selected, great, and you want to recreate your prototype. Some of our recommendation is you can definitely start with multiple EVK. It's probably a good way to try out different platforms to see what makes the most sense for you, because you all have different requirements. And another one I discovered recently that's pretty cool is the ARM Virtual Platform, which lets you essentially try out this platform online. They're virtualized, and you can enable your software team is one, but also test these platforms online and have all of that available even if you don't have the hardware yet. Second point is just getting familiar with your platform because you're going to spend a lot of time on it during the bring up, during the maintenance. So the more you're familiar with the ecosystem and everything, the better off you are. During the design, again, I'm not a hardware guy, so it's more like software-oriented recommendation. Take that with a grain of salt, but from our experience, I definitely involve the software people in the design because some of the issues that we see is if you pick up the wrong IC or the wrong peripherals, the bring up and enabling those can become very tricky and very long. So by just having that communication and validation, you can save a lot of time in the development process. And staying as close to possible as the reference platform. Keeping the default serial, for example, is one, because during the bring up, just seeing something on the serial is the first green light that says, okay, I have something, it's working. You know you have that base. That helps a lot. And USB, Ethernet, HDMI, those are big components that take time in general to bring up. And then you have all the reference distributions and the meta layers provided by NXP that are, of course, a great resource to leverage and provide a solid base. One architecture detail that I wanted to highlight for the software side is, again, in thinking about enabling your team, one architecture that lends itself very well to that is called the use case architecture. And the idea is if we take a coffee machine, something we all know, that would map to something like that, where at the core of your architecture, you'd have your core entities, data interfaces that you can use. So like, how do you make a coffee? Boiler, what's a pump, price, and users. Above that, you're going to have your business use case. So typically, how do you brew? One, how do you buy something locally, and how do you clean your coffee machine, for example? And then you have adapters and drivers. That's your platform abstraction, and by defining it that way, regardless of how you map that, you can move your software between one platform to another or continue developing even if you don't have that platform. And the use case orientation makes it very easy to see what the goal of the application here is, where you're going, and what the intent is. So in terms of maintenance and development, that's just a good way to organize it. And as you progress, you probably want to optimize your system. So you're starting with that reference distribution, and you want to have something more tailored to your needs. So the simple way to approach that is, well, you keep that, and essentially you trim down those packages, so you remove them from Yocto. It's, in general, simple to do. The limitation to that is because of the number of dependency and the number of the meta layers and everything, it's typically less stable than if you start from scratch, and it's a bit harder, of course, to get it to a small size on a device and as small as you need it to be. So the approach we generally recommend is to start a new distribution. You're still leveraging typically all the tools and the main components from your NXP distributions, so namely your kernel, U-boot, your machine, and everything, the main components that you have in Yocto. But now you're adding components instead of removing them, which means that you have a much smaller attack surface, much smaller size of your BSP, more stable because you're not removing things and trying to see if that works, but just adding, and Yocto will just add the minimum dependencies to meet that need. Requires a bit more knowledge, it's a bit more, I guess, scary is a strong word, maybe daunting, but it's the way to have the best distribution that you will want to have Yocto distribution for your platform. A couple of recommendations on 2 axes of optimization, boot time. You can spend like months working on boot time depending on your requirement. If you're automotive, you want to get that very low. If you're industrial, typically it doesn't matter as much. But some of the things you can do to reduce your boot time, removing unnecessary features. So that's, we're talking packages, we're talking drivers, we're talking logging. That actually takes a lot of time. And the boot delay that you have typically in your boot. Looking at more efficient way to boot, so looking at the storage that you have, the compression of the different stages, so you boot the kernel, the feed image that you might have, where is it stored, is it compressed or not, and how to best leverage your hardware to accelerate that. Delaying driver, which is done at the kernel level, and just in general looking alive, just for your customer to see, okay, there's something happening, even if you're not done booting. You have maybe your first bootstrap version of your application, you have something that make it look like it's alive and something is happening. And the second axis is the power consumption. For that, you can look at your clocks and adjusting those, of course. You can look also at the nominal drive mode for the i.MX, which is a way to adjust the voltage and overall the power consumption of different components. By default, it's running in a more, I guess, conservative approach for this voltage. And if you need to get down in power consumption, that's something you can play with to get it closer to your power requirement, power consumption requirement. Powering off the peripherals that you don't need, backlight, Wi-Fi, typically two big offenders, LTE if we had a modem. And sleeping and leveraging the Cortex-M is another one that we'll see after. That is a way to make tremendous changes in terms of power consumption. And now from optimization, we're switching a bit to security, and there's a couple of things that we wanted to highlight based on how we see that used. The use case for that are, of course, securing sensitive data that you have, preventing misuse of your device, and protecting also critical peripherals that you have connected to your device. Starting with this first one, Secure Boot. Probably know that, at least by name. Now it's pretty used nowadays. The why you'd use Secure Boot typically to prevent tampering your system from being tampered with. You are building a local root of trust, and that's based on the KPI. So you have your root key, you have different device keys, and you use that to sign your images. And that's typically vital nowadays for most of the system. If you have OTA, if you have any kind of system update, if you want to prevent that from happening from someone just plugging a USB stick or otherwise updating your system, that's the way to go. And there's basically two flavors depending on, for i.MX8, what category of device, processor you have, the i.MX8 and the 8M. The 8 is a bit more beefy, if we can say, on the security side. It's called AHAB, for Advanced High Assurance Boot. And the i.MX8 as the HABV4. NXP provides the CST, which lets you generate key, sign your binaries, and generate the blobs and the image that you need to flash with the right signature. And that root of trust and that keys that you generate here, that's basically something that you'll flash on your device. So if we look, if I enable that pointer, from your build process, the additional step here is that you're going to sign your image with this key once they're generated. Typically, I'll provide it 4. Recommendation is you keep 1. The 3 others you put in somewhere very safe, because you only have these 4, and once they are fused, and if the 4 of them are gone or lost, essentially your device is bricked. So out of those 4, you want to use 1, secure the 3 others. So you're going to sign that during your build process. You can do that locally. You can also do that in a cloud. So push an image to a cloud service that you have, which has access to a secure key vault, for example, and do that without having anybody access those keys. During manufacturing, that image is flashed, and you also fuse those keys for those 4 different keys. And then at runtime, that allows you to build that root of trust where from the get-go, the device is going to validate your first stage bootloader, your second stage bootloader, your kernel, and then you can build on top of that to allow even more security. So that's really that root of trust and a way to validate your full device. Recommendation here, make sure that you have a way to revoke your keys. So that could be through system update, through another way. If that first key, for example, were to be lost or stolen, you want to be able to revoke it. So you're going to have fuse that you can break to disable these keys. You just have to have a way to be able to revoke these keys. And then simple ways to build on top of that, you can enable file system encryption, making it read-only, squashFS, signing it, so you can really build all the way up top. The second one is trusted applications, of course. And why you need that, or why you could use that, if you want to build a software TPM, if you want to secure some peripheral access. So we're not talking USB, but for example, if you have an I2C, if you have an EEPROM, if you have any simpler peripheral, I would say, that you can communicate to and that you really want to secure. If you have confidential software IPs that you don't want to expose on the enclave, as you said, a non-isolated system. Or if you want to create a software-defined platform, which we heard about in the keynote, for example, that's also another way because you can customize your device tree at that stage and adjust that device tree to be able to enable the disabled device on your main Linux system and otherwise really not expose those. And it looks something like that, where essentially there are a lot of terms for the trusted applications enabling it, so I'm not necessarily going to go in there. From TFA to OPT to your trusted application, the change is at the boot. Instead of just having that first, let's say, chain, you have a second layer to it, which is going to enable your isolated system. And that trusted application, which you can see as, for example, in RTOS applications, typically a C application, it's very simple, that you can communicate with from your main system, and that can access protected hardware or have keys that are stored on the SNVS, which is the secure non-volatile storage that you have on NXP processors. Leverage all these different components to build really a security solution fully isolated from your Linux OS. Now, another thing that is important is to make sure the device is dependable. What I mean by that is that you can detect issue. I'm going to go very briefly about that. Recover from problems and be predictable. To detect issue, I think you know most of those, but you have a watchdog available. I have one or more, actually, watchdogs available on those systems, hardware watchdog, and those can be mapped on your Linux OS as well through systemd, for example, to detect any problem that happened from your bootloader to your kernel being loaded to after applications and restart your full system if something goes wrong. You have ECC memory protection that's available on some of the products as well. You can leverage Paron self-tests using it in the same way, either to do a hard reset or to have your device work in a degraded way. And you can use log management in general, multiple ways when you're looking at Linux, but journald and syslog, and having connectors to send that to the cloud, as well as tools like Firebase and Sentry, where you can have connectors to, on the application side, be able to catch crashes or errors and have a full context and log stack on your cloud dashboard. That's typically something you see for mobile applications, where mobile application developer will see when something's happening and have the stack. You can do the same for your C or C++ application and have this context, which saves a lot of time when you're troubleshooting or just looking at what's happening in the field and how you can help improve the product. From there, of course, you need OTA. I think I put it here because I have to, but I think all of you know that. A lot of different solutions, from off-the-shelf to not necessarily off-the-shelf, but you have Mander, SW Update, Rock, OS3. They all have slight differences. All those last three are open source, and Mander is a commercial solution, or at least partly commercial solution. And then you have either an A-B partitions to partition use swap with or without a golden image, which would be your out-of-factory reference image that you can always go back to. In addition to that, you can also have a recovery system that you can have. That's if you want to have, for example, a smaller rootfs. If things go really wrong and be able to start just from that minimal Linux, that's something you can enable. Supporting field updates, super convenient. USB, that can be done again with all of these, where instead of plugging from the cloud, you're just enabling that through USB with still the same way to secure it. Bluetooth is another great way to do that locally. You can enable ways to connect remotely. So we're talking, for example, reverse SSH dedicated BLE attributes. Something that you can also enable only on demand. So if you have, for example, a push button or something, a combination that you want to do on your device, only when a technician is here and otherwise not expose these interfaces, that's a great way to just remove these attack vectors and have those exposed only when the user or technician does something specific, which means you either do that live or you reboot your system into a specific mode to enable these. And then you have direct method, for example, from AWS IoT or Azure IoT to enable either immediate fix when something happens or just triggering actions, either pre-programmed or custom actions. And then you want to make it predictable. So you need something more real-time, and this is where it's great to have a Cortex-M on those. So why you want to leverage that? Well, if you have a real-time requirement, that's obvious. If you have low latency requirements, of course. If you need certification of some of the feature of your device, if you have low power scenarios, all of those can be solved by leveraging your Cortex-M. Basically looks like that, where you're going to have your Linux OS running on a Cortex-A, you're going to have your RTOS running on a Cortex-M, and then you have that channel here, which is based on remote proc and RP message. You have demo samples that are provided by NXP for that. But essentially, you have a channel that you can use to communicate between the two, and use it to essentially enable these scenarios, or as I mentioned, for the power management one. In that case, what happens is that you would sleep in your Cortex-A. The Cortex-M will still stay alive, and when a specific event happens, you would just trigger an interrupt and wake up your Cortex-A, either to enable connectivity scenarios or to enable some more complex actions, maybe show UI. So you can really have most of your work done on Cortex-M and just wake up the Cortex-A on demand. Just some of the details that I talked about that can be integrated in various ways, just as a serial port exposed at the next level as a serial port, or these different options. Now that you have that, you want to make it long-lasting. And what I mean by that, I'm going to look only at two different aspects, which is managing vulnerabilities and automation, and how automation can help you. Vulnerabilities, we know the story. Q1 of this year, it's 7,000 new vulnerability discovered, I believe. It's a lot. It's not new. The way to approach it here is you'd obviously start from an LT Yocto distribution, LT Linux if you can, so covering as much ground as possible in terms of lifetime of your different software components. The first step in that pipeline is to track those vulnerabilities and to get them. Yocto is able to generate a software bomb, a manifest, and you can use that manifest to query the NIST NVD, for example, or Ubuntu CVE, and get what vulnerabilities affect the software components that you have. The component in Yocto is called CVE check, and it's one way to do that automatically. You can also query that database manually. The output of that is actually you get a lot of noise because you're only using a subset of the functionalities that are affected on your product. So when you look at these vulnerabilities, you typically have a filtering or adjustment phase where you'll say, well, all of these actually don't apply to us. This is pretty important, and that we just don't use. So you have that filtering, and you can just store that either automatically or manually in a way so that the next time you run that loop, you know what really concerns you, and you can ignore all the rest, all the noise. And the last step is just you fix the issue. Typically, you grab the patches that match that one, apply that, and archive the results so that you can go back to it and know for each version what was affected and what patches were applied. The best way to enable that is then through automated testing, because if you apply those patches automatically, you want to be able to test your platform. I'll go quickly on it, but essentially having a pipeline like this will let you test automatically your device. You have a way to build that based on pull requests, for example. You create a pull request automatically with your patches. And then you can use local runners. GitLab is one solution, it's not the only one. You have a local runner that can be connected to your actual device, run those tests on your device, and get a yes, no, everything works, or here's the problem. Yocto exposes p-test that can be run. You have LTP, which is another project for test of the Linux kernel, and then you have dedicated tools as well. And if you don't want to have that constraint, again, you have this option, the virtual hardware. And for those maintaining Yocto, some tips here when you generate a release to tag and to archive the source so that you can make sure you can regenerate the same version. So if you tag a 1.3, for example, 5 years from now that lets you archive the source and all the origin, everything that you have, so that you can regenerate it and not just have an error because that remote broke and now you can't regenerate that version, you can't troubleshoot it. One way that we enable that on our side is essentially a pipeline like that, where you have GitHub or whatever source that you have here, using Yocto to build it automatically. We get the SPDX license from that. We get the software bomb. And we have one tool that we're using to filter that and make sure that you're not looking at thousands of vulnerabilities every time you run that loop, but only at the difference. And you can annotate those. And then Pluma is what we use for automated testing. JFrog is one that you can use to save artifacts, so your build artifacts, your reports, and everything that tracks through your release. And Black Duck is one that you can use to track your software bomb and your licenses. And finally, to our next section, because at some point, you're going to arrive towards the end of your lifetime, the lifetime of your product, it's going to be time to look at, okay, what can I reuse and what do we do there? Typically, at the end of the product, you're going to have code, configuration, infrastructure. You're going to have data in various forms. You're also going to have knowledge and know-how from your team. The goal is to reuse and retain all of those, obviously. The first option is just you abandon it and you start from something completely different. And the other is just you try to reuse as much as possible. That's obviously the goal. The limitation in our field is things, even though not as fast as like mobile or web, things are still evolving. So your Yocto version is going to change Linux, the packages, everything around it. And your next product might be in 10 years, maybe 5, maybe 15. So if at that point you're trying to port outdated software to that new version, that can be very challenging, and the decision might be actually, well, let's just stop and restart from scratch. In which case you're not reusing, not leveraging fully your platform and everything that was built before that. So what I think is a solution with small cost is essentially to have a platform approach and to re-switch the way you think about it. Instead of being a single product, even if it's a single product, to really see it as a platform that you're going to build and keep. So an example here, if you're looking at your first release and then 3 years and 6 years from now, today, this is the LTS Yocto version we have. In 3 years, the LTS is going to be the 4.4 because there's release every 6 months, so that's predictable. And in 6 years, it's going to be the 5.0. So you can plan around that, plan this migration, make sure that you can reuse that and design everything in a reusable way, and plan, so in that case, 1 or 2 major upgrades, which means that this path at the end is much easier because you don't have to work through 6-7 years of upgrade, which would be very difficult even for Yocto. You can just reuse directly what you had. Some of the upsides, reuse, of course, easier reuse, faster time to market, not the same. Working with newer technology, which is, I think, a good thing. You're going to leverage all the new features, security features as well. And that's yet another opportunity to delight your customers. And some tips to approach that, where you really need to have really a big picture approach. So you need to think about the hardware and how you're going to interface that. You need to think about your software, so the BSP and the application that runs top it. And ideally, you need to think about really the requirement and the needs across your project portfolio and not only looking at a single product. So quick answers. Under hardware, you could use and look at these generic interfaces like SMARC and OSM to build that, so that when you migrate to something newer, you can always reuse the same. For your Yocto platform, essentially you're building a platform for your BSP, and that's one way to architecture it. Instead of thinking product, you're thinking reusable layers, reusable distributions and features. So you can have a headless device, you can have a device with HMI, you can have a device with different features. And then on the application, one other way is to use the use case-based architecture to have reusable modules and libraries that you can easily port over and build something from. And the ideal step after that is actually the scale up, is to have a dedicated platform team where you become really a provider for all these different teams across your project portfolio, and you have internal release cycle and internal maintenance of these tools. And that's it for the core of that presentation. That's basically also what we do day in, day out, working on embedded products. So we do consulting, we do optimization, migration, all the things that we talked about, both at the low level, on the connectivity, and on the application side. And an example of product is that one that we work with Philips and Avnet, where essentially we had all the hardware design and work with Avnet. So the hardware and the display module. We worked on the BSP and the driver on those security approach. We developed the application, the graphical user interface, and the connectivity, and overall the platform approach, because same, they wanted to be able to reuse that across different products, of course. And I was also an i.MX8 with Yocto Linux Execute. Quick summary. We talked about that, getting started, some tips for organizing your system within power optimization, the security, with the two main points that I think you should leverage first of all, secure boot, obviously, and trusted applications. Making it dependable, so being able to detect, recover, and leverage that RTOS for all your key workloads. Long-lasting through automation and CVEs. And finally, reusable with your platform strategy. And then you get back to, here is a new product, let's build on a new technology, let's create something new, and you basically restart that, maybe with new bullet points, but that's the endless cycle that we're in, and that's part of the fun, I think. Thank you, everybody. That's it for today.